Okay, so let's take a look at an example here. So our example is going to have discrete eigenvalues. I'll explain what that means in a second. So you have to find the general solution of the system of linear homogeneous differential equations. And we're given here x prime equals 2x plus 4y and y prime equals x minus y. And again, we're assuming that x and y are functions of t. Okay, so step one is to write it in matrix form. So let's do that. Okay, so step one here is to write in matrix form. So to write in matrix form, the 2 here corresponds to the 2 in the matrix over here. The 4 here corresponds to the 4 here. The 1 in front of the x corresponds to the 1 here. And the negative 1 in front of the y corresponds to the guy here. Then you write the xy on the outside equals then x prime, y prime. Okay, now let's look at step 2. We need to find the eigen values. Okay, so step 2 then, to find the eigenvalues, we'll be taking a determinant of this matrix here. And let me just explain how I got it up here. Erase this. So on a matrix above here, the 2, 4, 1, minus 1, we're going to subtract lambda, 2 minus lambda up here, and then minus 1 minus lambda on the diagonals. That's how I got this guy down here. And then we're going to be taking the determinant of that. So to take determinant again, recall, we're going to multiply the 2 minus lambda times the minus 1 minus lambda. And then you're going to subtract that from 4 times 1, sorry. And that's how I got this guy here. Okay. And then if we multiply this out, we'll have minus lambda times minus lambda here. That's going to give my lambda squared. Then we'll have 2 times minus 1. And then we'll have minus 4. So I got the minus 6 here. You're going to have 2 times minus lambda and minus lambda times minus 1. Adding those, it'll be minus lambda in the middle. So I got that guy there. And you can check that factors as lambda plus 2, lambda minus 3. So then we can find our 2 eigenvalues. It looks like they're going to be lambda equal minus 2 and lambda equals 3. So let's write that. Okay, so we set each factor equal to 0. So we'll have our lambda plus 2 equals 0 and lambda minus 3 equals 0. So we have lambda equal minus 2 as one of our eigenvalues, and lambda equals 3 is another eigenvalue. Okay, so now we can find the eigenvectors. So let's do that next. Okay, so now we're going to use this augmented matrix to find our eigenvalues. This guy here. So we're going to put our lambda values in place of lambda. So we're going to have 2 augmented matrices to solve. Just look at, say, lambda equal minus 2 first. So putting minus 2 in place of lambda, we get the following. Okay, actually, I'm doing lambda equals 3 first here. So I'm going to put a 3 in place of lambda here and here. And that's how I got the guy below over here. So this guy here. Okay, so putting 3 there, you'll have 2 minus 3 and minus 1 minus 3. Okay, then it reduces to this. Now I want to solve this augmented matrix. So I want to get a 0 down here. So I'm going to go row 1, add to row 2 to give a new row 2. So adding these guys here and these guys here to give a new row 2. So negative 1 plus 1 will be 0 here. And 4 plus negative 4 will be 0 here and 0 here. And now we can use back substitution to solve. And the variables here we're going to call, I'm calling K1, that's the K1 column, and the K2 column. So this guy here would be saying -1 K1 4 times K2 equals 0. So let me write that. Okay, so again, we'll have a negative K1 plus 4K2 equals 0. And then solving for K1 here, we'll have then K1 equals 4K2. And K2 is free here, so it can be anything at all. So let's choose it to be 1. So putting 1 in place of K2 here, we'll have then K1 is 4. And that would be our eigenvector then. So let me write the eigenvector out. Hence, our eigenvector then will be 4, 1. It's basically going to be our K1, K2. So this is my K1 here. K1 is 4. K2 is 1. So let's verify that this is indeed an eigenvector. So let's do that. Okay, so let's verify that our 4, 1 is an eigenvector. So to verify, we take our matrix. Our matrix is 2, 4, 1, -1, multiply it by our eigenvector. So doing that, it'll be 4 times 2. That's how I got this guy. 4 times 4. So yeah, 1 times 4. Back that up. Then 1 times 4. So look at this guy. It'll be 4 times 1. So look at this one. And 1 times -1. That's how I get this one. If you add those, you'll have 8 then plus 4, so 12. And then on here it'll be 3. You can factor 3 out. It becomes 3 times 4, 1. And notice this guy here is the eigenvector. So eigenvector. And this is our eigenvalue. Eigenvalue. So it's the eigenvalue times the eigenvector. So therefore we verified it. Okay, so let's keep going. Hence, then define the solution corresponding to this eigenvalue. You take the eigenvector, and it'll be e to the lambda t. In this case, our eigenvalue is 3. So v1 equal to 4, 1. E to the 3t is the solution corresponding to lambda equal 3. Okay, so let's verify this. Okay, so it's verified. So our A times V1, well, here's my A matrix. I think I'll multiply it by my V1, which is 4, 1, e to the 3t. And above we did up here, the matrix times the eigenvector. The only difference here is we have an e. So the only difference is we have an e there. So it's going to be the same as above. So it's going to be 12, 3 with an e to the 3t there. You can factor the 3 out like we did up here. So it'd be 3, 4, 4, 1 e to the 3t. And note that you can write as 3 times v1. My v1's over here. Okay, now let's look at the derivative of v1. Okay, so let's take the derivative of v1. So v1's up here. So taking derivative, it'd be the derivative of my e to the 3t. So you'll take the derivative of 3t, which is 3. 3, so it'll be 4, 1, 3 e to the 3t. And that's exactly what we have here. So same. So hence then we've shown that A V1 equals V1 prime, and that's what it means to be a solution. So we verified that our V1 guy up here, this guy here, is a solution of our system. Okay, let's find now the second solution. Okay, so now we're going to find the eigenvector corresponding to lambda equals -2. So we need to then solve the augmented matrix. And how I got this augmented matrix is just my A matrix with the eigenvalue -2 on subtracted on the diagonal. It's going to be 2 minus a -2. So look at that one. And then -1 minus a -2. So that simplifies then to become 4, 4, 0, 1, 1, 0. And let's get a 0 now in this position down here. So we're going to go row 1 minus row 2 to give a new row 2. So doing that, you'll have 4. Well, actually, it looks like I should have went row 1 times 4 times row 2. Let me just change that. Yeah, so it should be row 1 minus 4 times row 2 to give a new row 2. When you did the operation anyway, you'll get a 0 on the bottom. And again, this guy is in the K1 position column, and this is in the K2 column. We can now translate these into equations. So doing that, we get the following. So I'll get 4K1 plus 4K2 equals 0. Then solving for K1, we'll have K1 then equals -K2. K2 is free, so I'm going to choose it to be 1. And then if K2 is 1, then K1 is -1. Okay, now we can write our eigenvector. So let's do it. So hence we can say our eigenvector then will be our K1, K2. So our K1 is -1, so it's -1, 1. That's going to be your eigenvector. And therefore, a second solution, V2, is going to be your eigenvector times e to the lambda t. Here, lambda is our eigenvalue, which is -2. So it'll be e to the -2t. So that should be your second solution. So now we can write the general solution. So let's do that. Okay, so now we've found our two solutions. The general solution then will be C1 V1 plus C2 V2. So in our case, our V1 is 4, 1 e to the 3t, and our V2 is -1, 1 e to the -2t, or here C1 and C2 are constants. Okay, so this is the general solution of our system. Okay, so we're done with this example. In the next video, we'll look at an example where we do not have distinct eigenvectors or eigenvalues, sorry. Okay, so let's leave it there.